Hello and welcome to homework 4, part 4. In this part of the homework, we're going to be taking a look at a similar process that we took a look at in the previous problems, and that we're going to take another look at the two tanks in series. So we have one tank that is draining into the second tank, and what we have done previously is that we've wanted to obtain H2, the height of the second tank, given some changes in the flow rate into the first tank. And what we did previously is done this by use of transfer function. However, what we're asked to do in part 4 of this homework is to pretend like we are solving for H2 by setting up the system experimentally. So essentially what we're going to do is we're going to have the inlet flow into the first tank, again that's draining to our second tank. We're going to have that at some steady state, and then we're going to give that some step change and then experimentally see how that changes the height in the second tank. Now what we're going to do, again, since we're not actually doing this experimentally, is we're going to make up some data here first to start off this part of the homework. So we're going to make 50 points of data, and what I'm going to do here is I'm going to add a block of code here. And what I'm going to do is I'm going to name a transfer function here called transfer function process. And if you remember back to our previous videos, the GP, the transfer function of the process, was this QC to Q2. So going from the inlet flow to the outlet flow, or the flow into the second tank, and then the flow into the second tank to the height in the second tank. This is all done by transfer functions here, right here, right? So what I'm going to do here is combine our process here. So I'm just going to multiply these together. So I'm going to do TF mult. Remember, we have our function to be able to do that. I'm going to go QC to Q2, and then Q2 to H2, right? And then what I'm going to do is we want to do a step change on our process, remember, to see how H2 changes. So I'm going to go TF process, and then dot step. And if we do this, what we're going to see is that we have our times here, and we have the response of H2 here in terms of deviation variable, so how much it deviates from the initial level that was at when we were running at a steady state. So what we can actually do here is specify the time periods that we want to do the step change under, or just what we want to grab out of the step change, really. So I'm going to call this time experimental for our experimental data, and we're going to go 0 to 15 and grab 50 points. And then what I'm going to do for our step change is set our time equal to t experimental. That's under case T. Okay. We have an issue here. Unmatched. Okay, we have a parentheses that wasn't supposed to be there. But now what I'm going to do is we want to be able to plot up our experimental data here. And we don't really care about the times because we're going to use our experimental times here. And I actually want to linearly space these out. So np.linspace. And what I'm going to do here is our second variable I'm going to call H2 experimental. Say that this is the experimental data that we are obtaining. Okay, so now what we can go ahead and do is plot this up. So I'm going to add a block of code into here, and I'm going to go fig is equal to make subplots. And then I'm going to add a scatter plot, so fig dot add scatter. We're going to have our x values as our time, so t experimental, and then our y values as our H2 experimental data points. And then I'm going to plot this mode as markers because we're saying that this is experimental data, so we want to see each of the points and where they were measured at. This is mode is equal to markers. Okay. Okay, so here's our plot. This is our experimental data that we obtained for the change of H2 given a step change um, in our flow rate going into the tank, our process here essentially. So what I'm going to do from here is that this data, it looks too clean to be able to have it as experimental data. So I'm going to add a little bit of error in our data here. So I'm going to basically make some random numbers and then make those numbers revolve around our data that's already plotted and then deviate them by some small margin just so we can make it seem like it's experimental data here so that we can manipulate it later on in this homework. So in order to do that, I'm going to, if I can go over here, create a variable here called RNG, random number generator. And I'm going to do np.random random state 1, 2, 3, and this will allow us to generate some random numbers. And then what I'm going to do is I'm going to do RNG.normal. I'm going to normally distribute these points and around our H2 values. So location is equal to H2 experimental. And then I have one more thing to put in here, which is the deviance essentially that we want from our location. So I'm going to put that in as 0.02. And I believe there's something that I need to call this here, I think. Or maybe I just close my parentheses. Let's see here. And I'm going to set H2 experimental equal to this. And what this is going to do is it's going to generate us more points. Okay, so what I forgot to do there was put in a scale at the end there, and that will allow us to get the standard deviation of those random points. I went ahead and did that. I will show that in a minute. But now that we have our experimental data, I just wanted to go back to our control loop here. And essentially what we have here is here's our control loop. And instead of like last time we had our process here, let's say this time that we do not know that. And again, we're going to go off our experimental data here. That's all that we have. Well, what we want here is if we just have all this experimental data, we can still want to possibly have a controller on it. So let's say we want our controller to be a PI controller. So if that's the case, we'll still need our gain, K, and 1 plus 1 over tau IS. So we're still going to need this K and tau I, right? And what we can do to be able to get this is that people have basically done a bunch of modeling with a bunch of data sets, and they've been able to give optimal values for K and tau I based upon certain data sets by using something called ITAE, which is the integral of the time-weighted absolute error. And essentially we can get this for a process that is a first order plus time delay. So that's an integral of time-weighted absolute error, and it's for an FOPTD, first order plus time delay model. Now, what you may notice is that the experimental data that we have generated does not look like it's first order, right? It looks like it's a higher order because we have some S shape to it, right? It starts up like that and then it curves out. So an exponential, right, or a first order will just look like that, right? It's 1, or it's a 1 minus exponential of t over some time constant tau. That's what like a first order plot would look like. But what we can do is we can basically approximate our data as a first order plus time delay system. And we can do this by essentially having the same plot here, right? Except however, it comes straight down. So we have some dead time here, basically when our data does nothing from here to here, and then it starts looking like a first order function here. So what we can do is we can essentially shift our data over some. So we'll have 1 minus exponential of t minus theta over tau, the time constant, right? And then what we can say is that, and this actually is multiplied, or no, that's right, yeah. Or no, well, I guess, yeah, we still have our k here. We have our, basically what we're going up to. So we have our k. So this is multiplied by k, right? And then this is multiplied by k. And then what we can say is that this is for all theta values that are, this is for all t's that are greater than theta, right? So for t, and then for everything else, we can essentially set it equal to 0. So for t less than or equal to theta. So it's basically shifting our data over to make it look like a first order plus time delay model, which then we can use this integral of the time weighted absolute error to get at being able to have a controller on our system that just has experimental data and no process. So let's go ahead and try to shift our data over into a FOPTD. Okay, so let's go ahead and define a function for our FOPTD model here. So I'm going to add in a block of code, define FOPTD is going to take in a vector of our parameters, right? Our k, our tau, and our theta. So v, let's go ahead and unpack that vector into our gain, tau, and theta. Is equal to v. And what we want to return, right, is our first order model here. So I'm going to create just a variable for it called y. This is our output. But remember that is 1 minus the exponential. So I'm going to go, we have Jackson imported, so I'm going to go jnp dot exponent, which is t experimental. And actually one thing I forgot here is that this is negative. It is negative t over the time constant. So I'll go negative t experimental minus theta, right? The difference of our dead time. That is then divided by tau. And then I think we need another parentheses here. Yep. That is then divided by tau. Yes. So now what we're going to do is then return. All we want to see, we don't want to see anything where our times are greater than theta, or when our times are less than theta. So we're just going to set everything that is less, all of our times that are less than theta equal to 0, just so we can get our exponential plot there. So we're going to go something like return jnp.where. And what this can do is we can separate out before theta. So if we go t experimental, our times that are less than theta, we'll set that as 0. Otherwise, it's y, right? Our function here. Let's go ahead and run that, and we can go ahead and plot this up over our experimental data here so we can transform this into an FOPTD. So let me go ahead and copy this down. Let's just add in a block of code here because we don't have enough already. And I'm just going to add another scatter plot. Our x values will still be our experimental time values. However, this time our y values will be our FOPTD. And we don't have our v parameters here because that's what we're trying to get at by doing this. So I'm going to supply some guess here at first. So if I go v guess, what we can do is we can set, let's see here, we can set k. Looks like our gain, we're doing a step change of 1 and we go up to 2, so that'll be 2. The tau here I'm going to set as 4, and theta I'll just set as 1. So then what I'm going to do here is do this in terms of v guess. Okay? And I'm going to change this to a line. Okay, so let's see here. Raised error. Let's go ahead and run this again. Receive value line. Let me just delete this out of there. See what it returns it as. Oh. Okay, so that was not the way that I was thinking it was going to look. I made one error, one obvious error, and another kind of typo. But I forgot to multiply our expression for our output here by our gain here, k. So I did that, and then I also had the negative just multiplied by t experimental instead of t experimental minus theta. So I brought that out. And then when I run it, you can see here our model looks a lot better. So this blue here again is our experimental data, and this is the model that we are approximating as a FOPTD. Okay, so I realized that our deviances in our experimental data got a little bit stretched too much there. So I went ahead and brought everything up into one cell just to run it at once to compare our model versus our experimental data. It does look a lot better now. I just changed the height and the width also as well, so it's not so stretched out. But now that we have our model, what we want to do is essentially we want to compare that to our data, and we don't want any difference between our model and our data. So what we want to do is we want to minimize the sum squared error. Essentially, we want to take the deviances, negative and positive, add them all up, and then square them, and then minimize them to be able to basically mimic our experimental data by our model. So in order to do that, what I'm first going to do is define a function to have our sum squared error. So I'm going to define SSE. That's going to take in a vector of our parameters. And what it's going to return is it's going to subtract our experimental data, it's going to subtract basically our model from our experimental data and then square that. And then we're going to add all of those deviations up. So we're going to go JNP.sum. It's going to go H2 experimental, and then we're going to subtract from that our first order plus time delay model, right? And then what we're going to do is we're going to square that. I need another bracket here. Okay. Now what we want to do is we want to go ahead and we want to minimize this sum squared error. So I'm going to go up and import minimize. It looks like I already did. So from SciPy optimize, import root. If we do comma minimize, we can utilize the minimize function. So I'm going to add in a block of code here, and I'm going to go minimize sum squared error, and we need to provide an initial guess. So I'm going to provide our initial guess for our v parameters. And what we see here is that this is what we get outputted here is these three values. So this is our k, our tau, and our theta that it basically suggests for us to supply to be able to plot our model over our experimental data to have it line up. So I'm going to go ahead and grab our result here by calling this result. And then when we make our plot here, instead of v guess, what I'm going to say is that this is in terms of our result evaluated at x.x. And what we can see here, res is not defined. Let me go ahead and bring that up here. So now we can see that our, for some reason this is not, let me make sure that this is above this. Get rid of this. So now we can see that our model fits our experimental data. So we have officially created our first order plus time delay model. Okay, so now what we want to do is we want to obtain the optimal controller gain and reset time from the ITAE. So in order to do that, I have this chart pulled up here. And what this ITAE integral of time-weighted absolute error tells us is that it basically says, so what we want is we want a PI controller that is optimized for set point changes. And what we can get out of this is it gives us some A and B parameters basically obtained from some experiments that people have done. And from these values, we can get to our controller gain and the optimal reset time. So if we look here, we have A and B. This P is our, this is what will get us our controller gain, Kc. So we have these equations down here. Y is equal to A times theta over tau to the B power. And then Y is equal to K times Kc. So we can solve for our controller gain here, Kc. So why don't we go ahead and do that. First one I'm going to go ahead and do is I'm going to set Kc, tau, and theta equal to our result evaluated at x, this right here. And I'm getting different values, very, very slightly different values to like the 1,000th decimal, or sometimes even the 10th, depending. And it has to do with the randomization of my data points. But since we're just making up the data points, I'm not going to give, it's not going to be too much of a fuss to me. But let's go ahead and calculate our controller gain here. So we'll have Kc is equal to, see what we have here. We have A times theta over tau I. So A is 0.586. So I have 0.586 times theta over tau. And then this is raised to B, which is, I believe, negative 0.916. Negative 0.916. And then this entire thing is then going to have to be divided by K. So put an extra parentheses there, extra parentheses there, and then divide by K. Oops, divide by K. Okay, so that's our controller gain. Now what we need to get is our reset time, tau I. And for tau I, what we have is down here in the bottom right. So tau I will be equal to A plus B multiplied by theta over tau. So A is, let's see here, 1.03, and then plus B, so 1.03 minus 0.615, because I believe B is negative 0.615, 165. And then that is multiplied by theta over tau. And this entire thing is tau, it looks like, is divided by this entire thing, because we want to do, yeah, tau is divided by this. So we have tau divided by, and that will give us Kc and tau I here. So that's how we obtain our parameters here from the ITAE. Okay, so now that we have been able to get our controller gain and reset time, The last step here is to actually use this in our closed loop system to install the PI controller and see how our system responds to a step change. So again, just to recap, we were able to obtain these values from basically grabbing some experimental data and then calculating them. So now we're going to use them in our closed loop, install a controller, and see how the height in the second tank responds. So what I'm going to do is I'm going to set tau d is equal to 0 here because we just have a PI controller. And before, what we were doing is specifying KC, tau I, and tau d. I'm going to go ahead and delete all of those because we now have our optimal values for our PI controller here of KC and tau I. Tau d is obviously 0 because we just have a PI controller. Now I think here I labeled KC as a capital C, so I'm going to go ahead and correct that. But let's go ahead and run our closed loop system here, see its response, and we're also going to rerun the Bode diagrams to see basically the stability of our system, see what our phase margin is, to see how stable we really are, to see if this was actually worth it. So let's go ahead and run these. So this is the response of our closed loop system, again, to a step change here. So you notice we go a little above our step change, we go back down, but pretty quickly we get a pretty accurate step change here just with the PI controller, which is interesting. And let's keep going down. Here is our frequency, and here is our Bode diagrams here. So you'll notice here that we don't really see ourselves getting down to 180 degrees. So let's go ahead and add some more values on our x-axis here. So I'm going to go, let's see here, let's go W is equal to np.log space. I'm going to go -2 to 2 and then plot 100 points. And then when we run our plot here, our Bode simulation, I'm going to specify our frequencies here. Okay, so a little bit better, and it looks like towards the end we're getting closer to -180 degrees, which would kind of raise a red flag for us. Not really, we would still have to look at our decibels diagram. But what you see here is that we do not get to -180 degrees, which means that is good in terms of stability, because if we got down to 180 degrees, what would we do is we would look at our frequency, and then we would go up to our decibel chart, go to the same frequency, and if our decibel at that same frequency was above 0, then we would be in trouble in terms of stability. Now, one last thing to note here before we close out the video is a phase margin. Now, what that is when our decibel here crosses 0, what we want to see is what is our degrees here for our phase lag. So it looks here that we're about at 0.5-ish. So if we go down to 0.5, let's see here, about right here. So we're about -120 degrees about. So that would mean that our phase margin is about 60 degrees plus or minus, which is good because that means we're basically 60 degrees away from any instability. But yeah, we'll wrap up this part of the homework. Thank you for watching.